Hello everyone, my name is Ian. Today I'm going to talk about Lancet, a system that can achieve better network resilience by designing for pruned failure sets. This work was done with my colleagues at Purdue University, Chuan, Ashish, and my PhD advisor, Professor Sanjay Rao and Professor Mohitawar Malan. It is challenging to design a network. One of the reasons is that we have to consider failures, which are inevitable in today's networks. Network failures are caused by many different reasons, such as planned network maintenance and unplanned events like fiber cuts or hardware and software bugs. It is also very costly when network failure happens. One well-known example is that 1 second of network outage could cost Amazon tens of thousands of dollars in revenue. On the contrary, network users want high service level objectives. They hope the network will be available most of the time. It's better to be 99.99% of the time or even higher. The key problem here is, how can we design a network for such stringent requirements? This problem has been studied for many years, and most of the existing solutions turn to designing for the worst case failure. Examples include R3 and FFC. The worst case design is nice that it tries to design a network which is robust to all possible combinations of F or fewer failures, but it has a weak point. If a single F failure scenario cannot be tackled, then we are forced to fall back to designing for F-1 failures only. Lancet is created with the hope to enable network designs beyond worst case, because the worst case design may be conservative. We are intrigued and motivated by the following question. Can we design for most F failure scenarios when designing for all is not possible? Let me explain using this toy topology. Here we have 5 nodes, and each link has a capacity of 1. Node S is the source and T is the destination. From S to T, we have a demand of 2, and we have 3 different paths to serve it. Take different scenarios involving simultaneous 2 link failures. For the one on the left, the network can still send 2 units of traffic, and for the one on the right, the network can only send 1 unit. Can we make sure that the good failure scenarios, like the one on the left, can still be handled? Lancet makes the following contributions. It provides a new approach to designing for most failure scenarios when designing for all is not possible. Lancet comprises the following key components. First, a novel divide-conquer algorithm, which can efficiently identify failure scenarios that a network can intrinsically tackle. Lancet also provides a compact representation of these scenarios, and I will explain why it is important later. Second, Lancet enables a linear program approach to designing protection routing which exploits this compact representation. Results show that this approach can cut the design time from more than 18 hours to 10 seconds for a real-world topology. Finally, validations on real-world network topologies shows the promise of the Lancet. So remember that we want to design for most failure scenarios when designing for all is not possible. But how? How to determine which scenarios to design for in the first place? So here we leverage an observation. Any routing scheme cannot perform better than the ideal scheme. So here the ideal scheme routes traffic using a multi-commodity flow model. Then we at least need to exclude those bad failure scenarios that even the ideal scheme cannot handle, and then design for the rest of the failure scenarios. Naturally, the next question will be how to find those failure scenarios that can or cannot be handled by the ideal scheme. Here, we use a divide-conquer classification algorithm to achieve this goal, and I will explain in the next slide. The diagram shows the idea of the classification algorithm. The goal is to identify failure scenarios that a network can handle. It is efficient, without explicit enumeration, and more importantly, it compactly represents failure scenarios in a small number of sets. We start with a set of failure scenarios. The algorithm classifies the scenarios into 3 categories by the answers to the following 2 questions. Do all scenarios certify? If the answer is yes, then we can classify the set to be acceptable or good, and we can stop here. The next question is, do all scenarios violate? If the answer is yes, then we can classify the set to be violating or bad, and stop here. So suppose the answers are both no to the questions above, then we will have to partition the set and repeat the process for each subset again. Now let's look at a concrete example of how this algorithm works. We start with the set of 0 failures and check, do all certify? Then the answer is yes. So we prune the set and mark it blue, meaning that the set has good performance. We next look at the set of all 1 failure scenarios, and similarly, the set certifies. The set of all 2 failure scenarios is the same, it also certifies. Now let's look at the interesting case of the set of all 3 failure scenarios. The answers to both questions, do all scenarios certify and do all scenarios violate, are both no. Then we partition the set. The way we partition is the following. We first find a link, in this case, link 2. We first find a link, in this case, link 2, and set the link status to be up or down. Here, 0 means up and 1 means down. So in a nutshell, we partition the set of all 3 failure scenarios into 2 subsets, with link 2 set to 0 or 1. We repeat the process with the subset on 0 branch. And we can see that the answers are again both no to the 2 questions. Then we have to partition again. This time, the set certifies. We mark it blue, prune it, and move on to the 1 branch. As you can see, the next branch, the next subset needs partitioning because it neither certifies nor violates. So we continue the process. In this case, we found the answer to do all scenarios violate is yes. So we classify the set to be violating and mark it red. Then we continue the process until the algorithm completes. This is a general description of the classification algorithm. In the next slide, we will look into how to instantiate the algorithm by specifying the 3 key procedures and how to make sure the algorithm is tractable. For the procedure do all certify, we show in the paper that it is NP complete. So instead of computing it directly, we get a conservative bound of the optimal value. So note that using a conservative bound does not affect the correctness of the algorithm, only the performance. And the bound quality is often good for practical networks in our context. Procedure do all violate is implemented with a simple feasibility LP to test if there is a good failure scenario. If we can find one, then the result for do all violate will be no. Third, for the partitioning strategy, we use a heuristic to choose a link L, which fails in many bad failure scenarios. Another important capability of the classification algorithm is that it can generate compact representation of failure sets. Look at the tree on the right, which is generated by the algorithm. The root node of the tree stands for all 3 failure scenarios of a 100-link network. The set A1 represents all failure scenarios that link 1 does not fail. So set A1, A2, and A3 together capture over 161K failure scenarios, and they all certify. We have 2 ways to represent these failure scenarios. The first one is to represent them in 3 sets, the union of A1, A2, and A3. The second way is to represent them with over 161K separate failure scenarios. We claim that the first one is better. To see why, we need to understand how it is used in formulation, and I will explain in the next few slides. Let's see how we formulate the design problem. We focus on designing link-based protection routing. To understand what link-based protection routing is, let's look at the toy network on the right. There is a normal traffic R on link ij, which starts from S and ends in T. So suppose link ij fails. The traffic that was on link ij is now rerouted on a pre-computed bypass path, link im and link mj. The rerouted traffic is expressed with variable p in the formulation, denoting extra traffic caused by link failure. So put it simply, a link-based protection routing provisions bypass paths to protect against each failure scenario. Protection routing is designed by the formulation H shown here, which solves normal routing R, protection routing P, with worst-case link utilization less than or equal to U. H is a generalization to a state-of-the-art protection routing scheme, R3. So in the formulation, the big X circled in red denotes the failure set, and the small x denotes a failure scenario. Recall that we mentioned earlier there is an issue with existing protection routing schemes. They only work when big X stands for all F failures. If the worst case utilization is greater than 1, then we're forced to design for F-1 failures. But what we actually want is to design for most F failures if designing for all is not possible. Now let's see how we can design protection routing with excluded scenarios. The key is in the capacity constraints circled in red. There are two ways to implement the capacity constraints. First, enumerate the constraints, one for each failure scenario X. Second, we impose the constraint for a union of the failure sets, each one represented using LP duality. So our approach, which is the second one above, is more compact in terms of number of constraints, since the number of sets can be exponentially smaller than the number of failure scenarios. While I won't have time to go through all the details, please refer to the paper for the method, how we can exactly reformulate H to a linear program. So if you recall, we mentioned that the compact representation of failure scenarios given by the classification algorithm is important. That is because it provides the failure set information we need here in the formulation H. So to summarize how we can design with Lancet, we can design a protection routing in 3 steps. First, we reformulate H to a linear program, handling arbitrary sets of failure scenarios. Step 2, we determine which failure scenarios to include with the classification algorithm. Step 3, we leverage the LP in step 1 and design a protection routing scheme for failure sets discovered in step 2. We next evaluate Lancet with real topologies as shown in this table. The largest topology we have experimented with has more than 150 edges. We use partial failure model throughout the evaluation. That means all links are composed of 2 sublinks, which can fail independently. We generate synthetic traffic matrix with gravity model. The first result we will look at is the performance achieved by the protection routing designed with Lancet, compared with other routing schemes on Geant topology. The blue bar shows the percentage of certified 2 failure scenarios in the ideal routing scheme. It tells that the ideal scheme handles 99.8% of the 2 failure scenarios for Geant. The performance of protection routing schemes designed for the worst case shows next. Here, we define Gen R3 of F to be the protection routing design obtained by optimizing worst-case F failure scenarios. The yellow bar shows Gen R3 of 1, and the red bar shows Gen R3 of 2. They each handle 87% and 12% of the two failure scenarios. The takeaway is the following. There exists large performance gap between the protection routing schemes designed for the worst case and the ideal scheme. So we next show how the design works with Lancet. The green bar shows that the protection routing design with Lancet bridges the gap and even reaching the optimal in this case. Now let's see how Lancet performs on larger networks. So here we define Gen R3 best to be the Gen R3F schemes, which with different F that gives the best result. So the figure shows that the Lancet, which is the green bar, almost achieves the ideal performance and behaves much better than the Gen R3 in all cases. Besides better performance, Lancet can represent a large number of failure scenarios in a small number of failure sets on all the networks shown in this table. For example, for Geont, Lancet can represent over 1,200 scenarios in 3 sets. The detail of how scenarios are distributed in the 3 sets is shown in the tree. For another example, for a larger network outcome, when considering 3 failure scenarios, Lancet can represent over 460K scenarios in 3 sets. This compactness of failure set representation is the key of Lancet's tractable protection routing design. We now look at how long it takes for Lancet and enumeration approach to design a protection routing. For a moderate-sized network Geont, Lancet can reduce the design time from over 18 hours to 10 seconds. And in addition, Lancet makes it possible to handle larger topologies in less than 2 hours. Lancet can generalize and extend to more applications. For example, Lancet can generalize to richer failure models like shared risk link groups. Lancet can also extend to designs with probability requirements or extend to design a protection routing with multiple traffic demands. There are more results on how to design with multiple traffic classes and validations on SC and testbed, and we will skip these in the interest of time. So please refer to the paper for the details. So to conclude, we show that the network design for worst case failure is conservative. With Lancet's efficient classification algorithm that yields a compact representation of good failure sets, we can design a protection routing scheme with performance close to the ideal performance. Lancet reduces the design time from over 18 hours to 10 seconds compared to enumeration approach. Evaluations and validations on real-world topologies show the promise of Lancet. So this will be end of the talk. Thanks for your attention. In case you have any questions or comments, please send them to the following email addresses. Thanks so much.